In this video, we're going to do what is needed before you even start this project. So we're going to cover some important telescope terms such as critical focus zone and Drawtube and so on. And as we work through these on an actual example, we will be able to determine step size, max steps, step mode, steps per revolution, step angle, and so on. All the things we need to be able to determine what stepper motor we will use and what driver chip we will use to drive that stepper motor. On top of all of that, you'll need to determine some other settings. You need to think about whether you're going to operate the controller as an access point or as a multi-AP able to log into multiple access points, or a simple station. Station is the only mode that will allow you to use duck DNS. So you have to put those things into consideration. MDNS requires the web server to be up and running in order for MDNS to work. OTA type, there are two basic types, the OTA server and the OTA running underneath the management server. And the PDF gives you a lot more details on those. Readwificonfig is basically a text file in JSON format which allows you to specify usernames and passwords that the controller will be able to use if a login attempt fails. A number of hardware options available to the majority of boards. All boards support display, home position switch and temperature probe. The PC boards also support in-out LEDs, joystick and push buttons. So if you've decided to use any of those, then the details for purchasing those are in the PDF. We come to some very important things, because all of these are going to affect the performance of the focus controller. So the things that we need to look at altogether is what focuser type we will use, that in terms of a board, etc. Max step, steps per revolution, step size, step mode, and once we know all of that, we'll be able to choose a stepper motor of the correct type or model number and the driver board required to drive that stepper motor. What we need to do now is calculate the Drawtube travel in millimeters. And you see here there's a full in position where it can't move any further, and also a full out position. And this happens on all focuser types. So what we need to do is we need to measure this to the nearest millimeter. We shouldn't go all the way into a hard stop, and we shouldn't go all the way out. So what we leave a little bit at the end, we leave a little bit at the beginning, and we take that to be the Drawtube travel. So we measure this, and we're going to use it to calculate max steps. Right, so here we've got an example for a Stellarview SB102T, which is one hell of a fine scope. And we measure the Drawtube, and the Drawtube goes from 0 to 6.5, it's rack and pinion, which gives us a usable travel of 5.5 centimeters to work with. The next measurement we do is we have a single speed knob here, and what we do is we rotate this one full revolution, 360 degrees. All right, so as near as we can get, and then we measure the travel again from where it was to where it is now, and we get 17 millimeters. Now the Stellarview SB102T is a focal ratio of 7.1. And if we multiply the focal ratio by itself and then multiply the result, by 2.2, we get a critical focus zone of 111. And this formula you'll see all over the web. We need 10 motor steps within the critical focus zone. So if we divide it by 10, we get a step size of 11 microns. Finding a Stepmode which exactly gives us 11 microns is a needle in a haystack problem. So what we're going to do is we're going to have a look at some existing Stepmodes and decide which one's close enough, and we'll use that instead. Right, so to calculate max steps, we're going to divide the length of the entire Drawtube travel by the step size, and we've already worked out the step size to be 11 microns, and we've worked out the draw travel is about 5.5 centimeters, which is 55,000 microns. So if we divide 55,000 microns by the step size, which is 11, we end up with a max step of 5,000. Right, so it comes a step angle, and this is something that I've been doing for some time but haven't documented. What we want to know is for a single step of the motor, what is that in terms of degrees? So to do that out, we're going to do a little bit of math. It's not that complicated. We know that 17 millimeters is the distance travelled in 360 degrees. So if we divide 17 millimeters, or 17,000 microns, by 360, we're going to get the distance travelled by 1 degree. And that is 0.0472 of a millimetre, which is 47.2 microns. Right, so let's work out what the step angle actually is. So in 1 degree, the Drawtube travel is 47.2 microns. If we divide that by the number of microns, if we divide the step angle by the number of micron travel, we'll get 0.02118. So 1 micron moves a step angle of 0.02118 degrees. So if we multiply that by 11, which is the motor step size, we get a step angle of 0.233 degrees. So we can now use both the step size of 11 microns or a step angle of 0.233 to determine which stepper motor and driver combination is going to be in the ballpark region. Right, so we've worked out those requirements. Now I'm also driving a filter wheel and a camera, and that adds a bit of weight to the imaging train. Choice became a NEMA planetary geared stepper motor because I want enough power or torque to be able to drive an imaging train that's got a filter wheel and quite a large camera attached. And if I don't choose a planetary geared, I just use a standard NEMA motor, it's not going to be able to drive the imaging train at all. So having decided on a NEMA stepper motor, I then have two choices. I can use a DRV8825 or I can use an LT98N. And I've chosen the DRV8825. We know what we're looking for now. And I have a look in the board types section underneath the user guide part 1. And I see that I've basically got three choices. I can use a PCB, I can use the TZT board, or I can use the terminal adapter board. And I'm choosing the PCB because this is going to be in a remote observatory, and I don't want any of the pins working loose, etc. on the TZT or the T adapter board. So I can go ahead and order the PCB, and I can go ahead and order all the parts now. But what we can't do is actually decide on the stepper motor that we've got, because we haven't done any hunting for the right stepper motor. So we'll do that now. So what we're going to do, there are a number of different types of NEMA paired stepper motors, and those with a paired stepper motor, they start at around the PG5 or 5:1 ratio. And if we look at those, and here they are, here's 3 PG5 choices. There's a NEMA 14, a NEMA 16, and a NEMA 17. And they all have a gear ratio of 5.18. They give a step angle of 0.35. What we're looking for is something a bit less than that, or a step size of 0.175 driving half steps. So this number of steps per 360 degrees is 1028. The holding torque, as you can see here, this is without the gearbox. With the gearbox, it's significantly higher. And you look at the difference in holding torque between a NEMA 14 and a NEMA 17 is nearly double. The amperage, and remember we're looking for amperage ideally less than 1. And the weight, you can see that the NEMA 17 is a wee bit heavier. And they also have different wiring. Okay, so the NEMA 14 has different coloured wires compared to the other two. So this one's not quite in the ballpark. The next one is PG14. Again, we're still looking for the same step angle. But you see here, every time we increase the PG from 5 to 9 to 10, etc., we're getting a step value which is significantly lower. This one here is a PG10 because there is no NEMA 17 motor for PG14. It doesn't exist. So I took the nearest one, which is around 10:1. And that gives, if we look at the number of steps per 360, it's 2000. And if we look at the step size, it's 0.18. So that's better than either of the other choices in PG14. And let me just go back and have a look at the PG5. The PG5 was 0.3, whereas the next one is 0.8. So this one would be closer to the value that we want. And last but not least is also the PG27. And you can see the step angles are getting quite small now. Why did I bother to show you the PG14 and 27 is because if you've got a very fast scope, you know, with a focal ratio of 2, well, definitely less than 6, the step angle that you're going to require gets lower and lower as the focal ratio comes down. And, you know, when you get down to F2, you are really starting to get things within this range. So that's why I put it in here. Okay, so we've decided on a PG5. We're going to run step mode 1, which is full steps. Okay, and we're going to plug this information back in now. Instead of using the step angle we were looking for or the step size we were looking for, we're going to use the step angle and the step size for the PG5. So we know that now that we've got 128 steps per 360, and we know what the step size is, 17 millimeters divided by that, so the step size is 16.5. And we work out the number of steps in the critical focus zone. 111 never changed, of course, but we now have a step size 16.5, and so we get 6.7 steps in the critical focus zone. And to work out max steps, as we divided, this didn't change, 5.5 centimeters. We divide that by the new step size and we get a max steps of 3,333. If we were to do the same calculations again, same Stepmode, but run the half steps, we get 13 steps in the critical focus zone. We get a step angle of 0.17, get a step size of 8.28, and we now have a max steps of 6,666. Alright, so to summarise everything so far, we did the math at the beginning and it gave us a step size of 11 microns and a max step value of 5,000 steps. But when we looked at all the Stepmodes that were available, we can't actually get that. So what we do is choose one that is reasonably close, and of course we could have done the calculations based on step angle. If I wasn't happy with any of those, I could then redo calculations using gears, but this is what we ended up with. So a Numa PG5 with a Deriving 8825 Stepmode with step mode set to 1. We got 6.7 steps in the critical focus zone and step size 16.5, max steps at 3,333. So for what we could basically do is just try that. 6.7 is getting a bit on the low side, but that might work. And over here, when we set step mode to 2, this is an alternative. So if we started off with step size 1 and we found out that wasn't very great and we weren't getting consistent focus runs, then we could very easily in software change it to half steps and then be able to use that. Don't become fixated on larger values for max step, because that's not the crucial parameter here. The crucial value is the step size. So it doesn't matter whether max steps are 3,000 or 30,000, it's the step size which is going to control how well the focusing occurs. Using half steps, the numbers come out to be exactly half the full step value, so it's quite easy to just divide things by 2 to get what it looks like at half steps. It's very important to do the math to find that correct step size value and then compare it against other motors that are out there that you can purchase and buy, which are going to give you a close enough figure to step size. And if you're using a heavy imaging train, you've really got no choice but to use a planetary feed Stepmode. And lastly, you always need to use a 12-volt motor for best results. It's pointless using a 5-volt Stepmode. That's the BYJ motor I'm talking about. Full steps is better for everything because you've got significantly more torque. You can run with coil power disabled, which generates less heat, and the DRV 8825 needs to be adjusted. There's a small pot which controls the power to the stepper, and if that setting's too low, the motor won't move or it jerks, and if it's too high, the motor gets very hot. And you do need to install a heatsink on the driver chip and make sure that in the case that you put the board and the driver chip in, that it has air vents to allow hot air to escape. The coil power I haven't talked about much, or if at all, but where you use micro stepping on a Stepmode, that is step mode 2, step mode 4, step mode 16, 32 and so on, each of those rely upon coil travelling through the stepper motor at any one time. And if you suddenly turn power off to the stepper motor, and a DRV8825 can do that, if you tell it to disable the coil power, what happens is the stepper motor will flip back or flip forward to wherever the nearest full step is. And that means you've now lost some steps which you can't get back. In the DRV8825, there is a special pin which we can use to disable the power going out from the driver chip to the stepper motor. And so it's possible for us actually to turn that power on or off by basically flipping a switch. And that's what coil power does. So for a motor that's got step mode or micro stepping enabled, you really need to run with coil power on. It doesn't need to be a planetary geared stepper motor, but if you're using micro stepping, coil power should be on. Now, if that generates too much heat for you, then that points to the small pot which controls the power to the stepper in terms of the current flow. That small pot needs to be adjusted. And there's plenty of stuff online to show you how to do that.